So we're looking at angular momentum. Angular momentum is like the rotational version of normal momentum. So how we have momentum, which talks about how hard it is to change translation motion. Angular momentum is to do with how hard it is to change the spin. So I hope you guys remember this kind of discussion wherein we spoke about a bullet, which is, say, sitting on a table. We are not scared of it. A bullet or sitting on a table, we have, I mean, they show in TV, that a bullet casing they have hanging across their neck and all of that. So, that being the case, people are not scared of it, right? So, bullet just on a table is not scary. While a bullet which is moving, obviously it's not, well, it's dangerous. As simple as that. Do you guys agree? So all of this is taken into account with the help of your mass into velocity, right? We spoke about truck and everything. So this is to do with mass velocity discussion. Mass discussion, I went on to explain a truck which is just standing and a truck which is moving. So this is okay, but this is not. You try to jump across. Anyways, point is, I hope you guys remember this. Now, similar to this quantity, which talks about all of this, we have your angular momentum. Basically, it tells if something is spinning, how easy or tough it is for us to stop it or spin it more and so on and so forth. Or if it's at rest, how difficult it is for us to spin. How difficult it is for us to change the amount of spin. So, for example, if you have a merry-go-round, okay, very big one, wherein we need machines. The point of us having machine is because we can't do it with hand. By the same merry-go-round, if it's small, right? Why, wherein kids are sitting and all of that. So I have done that. So it's doable. So I've done that to our nieces. So it's doable. So the one which with the machine and all that, it needs machine for that reason because it's big. It's not doable by a person, by an individual, basically. And if it's already rotating, say merry-go-round is rotating, and you have to be careful in stopping it. I don't know if you're stopped. If you spin it hard and it's already moving, to stop it, you have to be careful, and you should stop it slowly. I hope you guys have done all of that. And same thing if you just take a plate, right? If you just take a plate or a ball or something, basketball, you can do it on your finger and stuff. So you can rotate it. So the same thing can't be done with, well, okay, let me not go to any other idea. Or yeah, bowling ball. It's not so easy with on your finger for different reasons though. But anyways, point is heavier it is and quite a few other factors, difficult it is for us to make it rotate. If it's already rotating, it's difficult for us to make it stop rotating. So that all of that is taken into account with the help of angular momentum. Angular momentum is like that rotational version of momentum. So angular momentum of a particle rotating about an axis is defined as the momentum of the linear momentum of the particle about that axis. So let me explain. When it comes to formula, we have, well, I have 3 different forms. You can write it in many forms. So let me start off by looking at your vector form. So angular momentum is represented by L. I think I didn't mention it over here. Okay, no guys, please so make a mention that it's represented by capital L. So this is equal to cross product. Actually, let me write this off. So this is a cross product between your R and P. So here your R is the distance, and P is your mass into velocity, right? So this can also be written as m times of r cross v. So this is also okay. So this vector, right, this vector is perpendicular to both r and p. So the resultant will be, L will be perpendicular to the plane basically containing r and so I'm writing containing, it's out of the screen for you guys. Containing r and v or p or whatever, that is depending on the formula. So it is the direction of this, I'll be speaking about it given by right hand rule. So in terms of magnitude, we can rewrite this as, so mRV sine of theta, and theta is angle between r and v. Okay, so that is your vector form. Next is your, so I'll draw a draw diagram. Then you guys will remember. I hope you guys remember lever arm. So L is equal to m v d, where d is r sine theta. That is the shortest distance from the origin to the particle's velocity vector. So this is shortest distance, this as in d is the shortest distance. Again, I hope you guys go back to your few pages and have a look. From the origin to the particles velocity vector. Okay, then we have your determinant form. I think that's the last one. So yeah, this you guys have to learn matrix, but from here you can derive this few other forms that you can derive. So this is better off. Knowing this is better off. So ijk, your vectors, unit vectors, that is, and your r and your momentum along the respective direction. So this is your component of your r, right? And this is component of your momentum vector. Okay, so those are your formulas. Then we look into direction also in this video itself. So for a case of theta and 180 degree, what happens? For that, I need to go back to this formula. So case when theta is equal to 0 or 180 degree, what happens? Yes, L is 0. And for theta is equal to 90 degree, yes, L is maximum. It makes sense, right? I hope this makes sense. Okay, so if things are, 90 degree, means you have the maximum rotational effect, right? This we have seen. So that is continued over here. Nothing fancy over here. Again, guys, all this is commonsensical. Don't learn it as a separate unit. Use common sense, use general observation. The concept is done. Now, when it comes to direction is always perpendicular to the plane formed by R and P. I think I mentioned it over here. Where did I mention it? Yeah, plane containing R and P or V. So it's determined by, I have not written V over here, but it's so true for V also. I have mentioned it over here. So, determined by right hand rule. What does right hand rule tell? Point your fingers in the direction of R. Curl your fingers towards P or V, the second vector. Your thumb will point in the direction of P. Okay. So let me do that for you guys. Not this. Say you have your X, Y, and Z. Your position vector, your R is over here. And you have your momentum in this direction. And we know that we need to extend this for discussing about the angle. So theta or something. And then when you resolve it and stuff, this is the one which matters to us. Okay. So this is the one which is perpendicular. Right? And what else? Yeah, I think that's good enough. So what I want to tell is, yeah, if I shift this R perpendicular to this space, it's something like this. Not R P perpendicular. Your L will be in this direction. Okay, so L will be in that plane. This can be any X, Y, or Z. I don't want to mention anything. I just want to keep it open. This can be X, Y, Z. This can be Y, X, Z. Sorry. Yeah. No. X, Y, Z. Then I want to tell Y, Z, X. Things like that. So in all this while, I'm using right hand rule. So you have to point your fingers first in the direction of R and then bend it in this manner. So this is pointing in the direction of L. And finally, you have the SI unit. Where should I mention? I'll mention it here. So SI unit is quite simple. So you have meters, then you have kg meter per second. So this is nothing but kg meter square per second. So this would be your SI unit, and dimension and stuff, you guys can do that. So yeah, that is your brief introduction to angular momentum. So this is your momentum. If you guys want to write it, this is related to angular momentum. This is your formulas actually. And I think I didn't miss. Oh no, I did. Direction part.